see the first set of examples. This is to look at what is the Nyquist rate, Nyquist sampling rate. So, first example, we will call it as example A. The continuous time signal given to us is a sinusoidal signal which is sin 200 pi t. Okay. Now, this is of the form sin omega naught t. So, omega naught is equal to the discrete time, the continuous time frequency is equal to 200 pi. Okay. Now, the typical form of continuous time frequency is 2 pi f naught. So, basically you compare these two, you find that f naught is equal to 100 hertz, right, f naught equal to 100. So, you compare this and you say that okay, so the continuous time frequency is 200 pi, this will be radians per second, and this will be in hertz, f naught will be in hertz. Now, the Nyquist sampling theorem says what is the highest frequency which is present in your signal. In this case, there is only one frequency that is present, that is at 100 hertz. So, the Nyquist frequency, the sampling rate. So, Nyquist rate, given that you know that the highest frequency, so then we say that the Nyquist rate, or we say the sampling frequency must be equal to 200 hertz. Hope you are comfortable with that. We looked at the expression for the continuous time signal, it was a sinusoid. We derived the continuous time frequency in radians per second. From there we went to the frequency in hertz, and using that we wrote down the sampling frequency. Okay, so sampling frequency is something that we will specify in hertz. So maybe we should write it as Fs. Okay, the corresponding omega s will be equal to 2 pi times Fs, that will be equal to 400 pi. Okay, whatever is the highest frequency, if 200 pi radians per second, the sampling frequency will be equal to 400 pi. So, again we can also say that in this case, let me just use uppercase Fs to be consistent. So, this is Fs, this is Fs, and so we have the full representation that we have. Now, let us look at some simple extensions of this problem, again just to get comfortable with the applying of the Nyquist criterion. If x of t is equal to sin squared 200 pi t, sin squared. Okay. Now, you know that you can write down sin squared as 1 minus cosine 2 theta. So, this will be cosine of 400 pi t, the whole divided by 2. So, now you have two signals, one is a constant, the other one is 1/2 of cosine 400 pi t. Okay. Now, we can look at this also as a periodic signal, because it is equal to, it's a constant, and this also. So, in terms of the highest frequency component, the DC term does not have any frequency component, as frequency is 0. So, we look at the second term, the highest frequency component f naught will be equal to 200 hertz, just like we did last time. So, then we say that the Nyquist rate sampling, Nyquist rate Fs will be equal to 400 hertz, Fs equal to 400 hertz. Okay, always double of the highest sampling frequency. Now, simple trigonometry which I am sure you are quite familiar with. Supposing I say that x of t is equal to cos cubed 200 pi t. Okay, again rewrite it. You can write it in terms of cosine theta and cosine 3 theta, and you can verify that in this case the sampling frequency will come out to be 600 hertz. Okay, you can look at the expressions and do that. Let's look at a little bit more cases where the application of the Nyquist theorem requires a little bit more insight into the signal that we are working with. So let us take a look. So this is example number 2. Example 2, we are given that x of t is equal to sinc 200t. Okay. Now, the definition of sinc is sine of the angle or the argument multiplied by pi. So, it is sine of 200 pi t divided by the argument 200 pi t. Now, this is what is compactly represented as sine 200 t. Now, the question is, what is the highest frequency component in this particular signal? Now, of course, there may be a tendency to say, oh, I see sine there on the numerator. So, therefore, the highest frequency component is 100 hertz. So, let me say that the sampling frequency should be 200 hertz. But I would like you to be a little bit careful in this one. So, let us say what is the correct way to understand this particular one. Now, what we would like to do is we would like to know what is the frequency transform or the Fourier transform of x of t. Okay. Now, you may or remember from signals and systems that there is a very simple transformation, but even if you do not, let me just ask you to do a simple exercise. Supposing I tell you that there is a signal whose Fourier transform is given in this fashion. Okay, this is x of j omega, the Fourier transform of a signal. It goes from minus 200 pi to 200 pi. This is in terms of the radian frequency, and the height is equal to 1 by 200. Okay, I would like you to find the corresponding, let us call that as x1. I want to find out what the corresponding time domain signal is. And the way we would do it is do the inverse Fourier transform, 1 over 2 pi minus 200 pi to 200 pi. The scale factor is 1 over 200, it is a constant, there is no other function, e power minus j omega t and d omega. Okay, and so this would be the representation for the inverse transform. So, if you go through and do the integral and substitute, what you will find, you will get is sine of 200 pi t divided by 200 pi t. Okay, yeah. So, if you put as e power plus j omega t, again the integral will come out to be the same. So, we can verify that this is the case. Okay, so so this particular signal, the corresponding time domain signal is x1 of t, which is given by sinc of 200t. Okay. Now, sinc 200t, what is the highest frequency component? Now, you can confidently say that it is a rectangular Fourier transform, and the highest frequency component is 200 pi. You do not have to guess it, you can tell the exact. So, we can write down here saying the highest frequency component of this signal omega n is equal to 200 pi, then the corresponding frequency f naught is 100 hertz, and this means that the Nyquist rate sampling frequency must be equal to 200 hertz. Okay, so I hope you are comfortable with that. Now, let us look at some extensions of it. Again, this is more to familiarize yourself with the signals and just the way of thinking about signals and about the frequency content of signals. So, a variation of this, if I tell you that x of t is equal to sinc squared of 200t, that means sinc times sinc. Which is the same as saying you are multiplying sinc 200t with Sinc 200t. Okay, so basically this is Sinc squared. Okay, and if you look at this in the transform domain, it will be a convolution. So if you had x of j omega, it will be convolved with itself, x of j omega. So which says that you take this rectangular function which goes from minus 200 pi to 200 pi and convolve it with itself. Okay, so what we are saying is this is one rectangular function convolved with another rectangular function. Okay, rectangular convolved with rectangular, I hope you are familiar. So this will give me a triangular function, and the limits in this case are minus 200 pi to 200 pi. The second rectangular function is minus 200 pi to 200 pi, and the triangular function will be from minus 400 pi to 400 pi. Okay, so if your highest frequency component omega n is equal to 400 pi, then f naught is equal to 200 hertz, then the Nyquist rate will be Fs equal to 400 hertz. Again, simple applications. And maybe one more thing that you can try out. Supposing I told you that the signal x of t was Sinc 200t plus Sinc squared 200t, addition of two signals. Okay, we want to look at what is the highest frequency component. Of course, you can argue that it will be based on Sinc squared, which is correct, and this will tell you that in this case also this Nyquist rate will be equal to 400 hertz. Would like you to verify that. Now let us take it a little bit further to understand and expand on what we have been talking about. Okay, now this is example 3. And this will require you to visualize what is the processing that is happening, so that then we can apply the Nyquist criterion in a very careful manner. Now, the first thing that I would like to discuss with you is what is a low pass filter. A low pass filter is a filter. So, if you look at it in terms of the frequency response, h of j omega magnitude, the magnitude response of a low pass filter, ideal low pass filter, looks like this. So that means it has a gain of 1, it passes those frequencies all the way from minus omega c to omega c. Omega c is called the cutoff frequency, Now, this is a very important type of filter, because this is the one that helps us remove unwanted high frequency noise, interference and other things. So, this is called the cutoff frequency. Okay, the purpose of a low pass filter is to keep all frequencies between minus omega c to omega c and to discard all frequencies which are above omega c. That is the property of a low pass filter, 0 being the lowest frequency, all the way from 0 to omega c are the lower frequencies, above that we are going to reject. So, the problem statement that we are having is that we have a continuous time signal xc of t. Xc of t is obtained as the output of an ideal low pass filter, obtained at the output of an ideal low pass filter, ideal low pass filter, okay, with cutoff frequency omega c is equal to 1000 pi. Okay, so just for you to visualize, so you can think of the original signal as having some frequency content from minus omega n to omega n, when it passed through the low pass filter, what was retained was only from minus omega c to omega c. Okay, so the rest of it got, so when they say that you are looking at the output of a low pass filter with omega c, you are thinking of a signal that looks like this. Okay, so it looks like this and has a limit at omega c, no frequencies above omega c. The original signal, the blue signal, had frequencies above omega c, but at the output of the low pass filter, this is what you are seeing. Okay. Now, what is the Nyquist criterion in this case? Same principle. You go and look at your signal. So this is x c of j omega. What is the highest frequency component? So write down highest frequency component is omega c, which is the cutoff frequency, which is equal to 1000 pi. In terms of the highest frequency f naught, this will be equal to 500 hertz, right? And so that basically tells us that the sampling frequency must be equal to 1000 hertz or 1 kilohertz. The sampling period Ts must be equal to 1 over Fs or 10 to the power of minus 3 seconds or 1 millisecond. Okay, so this is the same as saying that your sampling period is 1 millisecond. Now, can I do a sampling rate which is half a millisecond? Will it still satisfy? Go back and visualize. We said there is a Nyquist period, right? Basically, anything less than the period or higher in frequency. Higher in frequency means the period is going down. Anything higher in frequency is okay because we can still recover the original signal. Anything less than the Nyquist sampling rate, we will not be able to satisfy. So the question that is now being asked is, which of the following sampling periods, following values of the sampling period Ts will guarantee that we can sample and recover the xc of t without loss of information, will guarantee that xc of t, that output of the low pass filter, will be recovered without loss of information. Without loss of information. Okay, this without loss of information in the process of sampling. Okay. Now, since we already have the basic foundation on how to apply Nyquist criterion, all we need to do is make sure you understand the context in which the problem has been stated. It says that the output of a low pass filter, that means only up to the cutoff frequency will be present in your signal. That gives you also the highest frequency component of your signal. That tells you what the Nyquist frequency is. So therefore, we can now check and see. So if I tell you that the first case that I want you to look at is a sampling period which is 0.5 into 10 power minus 3. That means this is equal to 0.5 milliseconds. We know that 1 millisecond will work, right? That satisfies the Nyquist criterion. If you sample at a faster rate, that means sampling period has gone down, do you think you will still be able to recover the signal? The answer is definitely yes. So in this case, you will be able to recover the original signal because you are over satisfying the Nyquist criterion in this particular case. Okay, let us take a second case. Ts is equal to 2 into 10 power minus 3, that is 2 milliseconds. Okay, what is the Nyquist period, Nyquist frequency, and is 1 kilohertz. The Nyquist period is 1 millisecond. 2 milliseconds is far larger than the Nyquist condition allows. So therefore, this is a case where you will not be able to guarantee that you can recover the original signal, because this one violates Nyquist criterion. Okay, it violates Nyquist criterion. I hope you are able to see that, and also sort of apply the condition. Okay, let us take one last example. Third example, Ts is equal to 10 to the power of minus 4 seconds, which is 0.1 millisecond. Okay, 1 millisecond is what we need. 0.5 itself is even better, we can satisfy. 0.1 even better. So of course, this will also be a case where we can satisfy the Nyquist criterion. Okay. So with this, I think we've sort of had the ability to do a good practice in applying the Nyquist criterion. Now, one of the key things that you will recognize is that in every case, the Fourier transform, continuous time Fourier transform, plays an important role.